episode 123, Exomoon Expectation. Emily, welcome back to Syzygy. We haven't done this in a really, really, really long time.
Far too long.
What's been going on?
Well, there's this thing called summer.
Oh, yeah.
Yeah.
Thing like summer holidays and families and international travel. What have you been up to?
Yeah, I had a couple of trips, had some worky trips. So I went to our main astroseismology conference in Porto in July. That was exciting and very informative.
Very nice. I mean, a conference is always nice. A conference overseas is even better. For various definitions of overseas, I guess it's just across the water, really, from the UK.
Yeah.
And Porto's a really nice town.
Beautiful.
If you've never been there, Porto in Portugal, great place.
Yeah, absolutely loved it. And nice to catch up with a lot of kind of science friends as well.
Mm-hmm. Very cool, very cool. Anywhere else over the summer period?
Did a little stint in the Lake District.
Nice.
Just a little one closer to home. That was nice.
Very nice, very nice. I had a month down in Australia, which was really nice. Always good to get down to the Antipodes. But yeah, summer's over and we're getting back into the swing of things here in Syzygy.
The nights are drawing in.
Yeah. It's getting darker outside, which must mean it's podcasting time. So thank you to everyone who's stuck around. We are continuing with this podcast. It hasn't died. Definitely still a going concern. And today we're going to be visiting something which we touched on a little while ago. Way back in like episode 19
Yes, that's
of
right.
this podcast, which was when, Emily?
October 2018.
Like, that's ridiculous.
Yeah.
Like, we haven't been doing this that long, have we?
No,
Apparently-
I'm sure we haven't.
Apparently this is true. And the topic is not exoplanets, but exomoons. Moons going around exoplanets. Moons going around planets, going around other stars. Emily, it's been a while since we touched on this topic. Why are we talking about this today? What's going on?
Well, just in the last few weeks, there's been quite a lot of interesting stories come out about potential exomoon detections. Now, surprisingly, I would actually say, since October 2018, when we did the last podcast, in that podcast we talked about a candidate that had popped up that might have been an exomoon. And I guess we kind of maybe left it that saying, well, we'll confirm this soon.
Sure.
6 years later.
How long could it possibly take?
6 years later, we've got a few other candidates. I won't say lots. There's a handful of other candidates. We still haven't got a confirmed exomoon.
Really? We still don't have it? Like, none have been definitely put a pin in that one. We've got it.
No.
Wow.
Every single one still has a question mark. And indeed, there's a new question mark moon added, as I say, in the last few weeks. This is WASP 49b. And there's also some news that we just picked up through the various interwebs that there's another candidate that's being observed, has been observed in the last week or so, that is pretty promising as well.
Right.
So we may be on the cusp now of this firm, yes, here is our very first exomoon.
Isn't that amazing? I mean, it's like that's, how many years? 6 years later. And at the time when we did episode 19, we would, I might have imagined, okay, well, I'm pretty sure we'll be able to confirm this one fairly soon, maybe within a year or two. It just kind of shows, I guess, how hard it is to spot something going around something else a really, really, really long way away.
Yeah.
So I guess we should probably touch on that today.
Absolutely.
Is just how hard is this problem? All right. So where shall we begin this? Do we need a little update on the status of how do you hunt for an exomoon?
Yeah. Okay. So an exomoon is by definition going to be smaller than an exoplanet, right?
Yeah. I guess if it's the other way around, you've got your names wrong.
Yeah. That's right.
If the moon's bigger than the planet, then swap the terms.
Yeah.
Yeah.
So an exomoon, it's a moon-like object going around, or a natural satellite of an exoplanet. Now, that's not necessarily to say it's small. I mean, we think about moons as being small in our solar system because I think the biggest one is something like a third the size of the Earth, something on that order.
Which one's that?
Ganymede.
Okay. But that's going around a honking great planet.
Well, yeah,
so,
that's going around Jupiter. But we know that we've got, 300-ish, nearly 300, let's say, moons in our solar system.
300 in our solar system?
Yeah.
Holy cow.
Yeah.
That's a lot bigger than I had. I knew that there were dozens and dozens, but 300?
Yeah, nearly 300. I think Saturn has kind of nearly half of those.
Seriously?
Yeah.
Wow. Well, I guess, it's got the rings, right? And so it's got form in that regard. Saturn's
Indeed.
got stuff going around it.
Yeah.
Is that why, by the way, just as a quick aside, did something happen with Saturn that gave it the rings and lots of planets?
Probably.
Yeah?
Yeah. Well, probably some of the planets predate the rings, but many of them will be linked to the process of forming the rings, which was some kind of interaction with some kind of thing.
Right.
Sometime in between the dinosaurs and us.
Something happened.
Yeah.
Something happened. Okay, cool. Well, 300.
Yeah.
Point is, moons are aplenty.
Yeah.
Right? Once upon a time, we didn't even really know whether or not the solar system in terms of planets was normal and ordinary. And now we've kind of established, planets are everywhere. On average, look at a star, it's going to have a planet. Mm-hmm. Yeah? We're now trying to figure out, how common are moons? And our solar system, it's got a lot of them. Mm-hmm. You've got to assume if you're going to have planets, you're going to have moons.
Yeah, exactly. But we've not found any, even though we've known about the moons in our own solar system since, Galileo, right?
Yeah.
He's very famously looked at the moons of Jupiter.
Yeah. Let alone our own, which is fairly obvious.
Well, yeah.
I think that was known before Galileo.
That might have been known beforehand.
Yeah.
True. Anyway, so the problem is they're really hard to find. We've gone on and banged on about how hard exoplanets are to find.
It might have come up before. Yeah.
And it's very easy to take that for granted that 20, 30 years ago, exoplanets were like the edge of impossibility. And that's kind of, I feel like, where we are now with exomoons. But they're so hard because they're naturally smaller than exoplanets, so they have less gravitational influence on whatever you're trying to measure their gravitational influence on, and we'll come back to that. They have no light that they emit of their own accord, much like an exoplanet doesn't emit light. Only stars emit light. So you've got to use these slightly indirect techniques to pick them up because you're not getting a direct signal of light from these very small things.
Yeah.
So I looked at we've got about 20 candidates, at least there's about 20 that are listed in Wikipedia at the moment, of exomoons. Some of those are sort of quite no, they're probably not, but
okay.
Some of them are still, maybe.
But that's 20 out of, what's the current tally of known, confirmed, definite exoplanets? Last I remember, it was in the thousands, well and truly into the thousands.
I think it's just above 4,500.
Right. Okay.
Yeah.
So out of that 4,500 ish, 20, maybe some, probably not, potential candidates for exomoons. Yeah. This is hard.
It's really hard. Yeah. So ways to find them. I've got 7 actually, which were from that list of just 20. So there's different things you can do. You can coming back to Saturn, you can do the Saturn approach where you look at a planet that's got a disk and you look for gaps in that disk, or rings.
Sure.
So Saturn has a beautiful ring system. There's some big gaps in that ring system which are caused by resonances with some of its moons. So even though you can't see the moon itself, you can see this big gap.
Okay. And that makes sense. I can see that. But my immediate question is, that assumes we can see planets that have rings? Aren't you just shifting the problem? Is it, all we have to do is look for planets with rings and then look for gaps in the rings, and that's probably a planet. Yeah, but you got to find the rings first, right?
Which is tricky. We do have more disks than rings. We've found a few planets with circumplanetary disks.
Okay.
So these are kind of just big, broad blobs that they've accreted from probably the leftover remnants of the stars forming.
How do you know that? How do you see that? You
can see them in the infrared. So, because they're nice and warm. So it's like warm dust.
Right.
You can see them. Yeah. So you can see them there. This is one we're going to come back to because it involves some of the planets we're talking about, planets and moons we're talking about today. You could do transits, direct transits. So a transit for an exoplanet, which is our very, very favourite way to find exoplanets.
That's the most common way, isn't it? Most common
way, definitely. Yep. So you wait for the planet to move between us and its host star, so transit across the surface of the star. You get a very small, typically 1% drop in the light that you receive from the star. Now, if that planet had a moon, and if the moon was in the right place in its orbit and at the right time, you might get a tiny little extra drop.
Right. So you're looking for a tiny little extra bump in the drop, tiny little extra drop on top of something which is already really quite hard to see.
Yes.
Right. I mean, the images that you see in sort of YouTube videos and stuff that show how this works shows here's the light from the star going along on a graph, and it's going along, and then it drops down quite dramatically when the planet goes in front of it. But it's not like that.
No.
Is it? It's
No.
it's a very small drop of what?
Yeah, about 1%.
About 1%. And so you're looking for maybe 1% of 1%?
Yeah.
Wow, that's not easy.
Yeah. And much like it's easier to find bigger planets because they have more percentage drop, it's actually easier to find bigger moons.
That makes sense.
So some of the potential detections, one of which is what we'll come back to, that's an interesting system, they're things like several times the mass of Jupiter with moons, doing air quotes here, moons that are about the size of Neptune.
Right. So the ideal would be I don't know, I mean, does the size and the brightness of the star, I guess brightness of the star makes a difference, but a star with a honkin' great planet so that you can really easily see the dip, but which also has a honkin' great moon going around it. And how common might that be?
Well, it's very difficult to say because these hot Jupiters are, as the classic word for them, these very big planets that are very close to their host stars, so very easy to detect,
right?
Or at least easy comparatively.
Because they're nice and close, so they're going around like often.
Yeah,
they're really whipping around,
and they're big, so that they block a lot of the star's light, right? So, and they're close, so they block a lot. So all those things make them easier to detect. The problem is that the gravitational way of getting there, well, we don't really know exactly how hot Jupiters end up there. They're not born there, that close to their host stars. They probably traverse to that position somehow, whether that's through some kind of orbital decay, resonances and so on, or capture is kind of the other scenario. Both of those options they disrupt the gravitational dynamics of having a moon. So if you just tried to take, for example, our Jupiter and just nudge it in closer and closer and closer through some dance of gravitational dynamics.
Sure, let's say that's possible.
You'd probably lose all your moons along the way.
Right. And that's because you're getting closer to the star. The gravitational forces are much greater. Things are moving much faster. It's kind of hard to get a nice, stable...
Partly, but it's also you're disrupting somehow. So
I see.
You've got interactions with other big planets. Like let's say you're using Saturn's gravitational interactions to move Jupiter. You're going to disrupt the moons. And if you move the moons outside what's called the Hill sphere, which is kind of like, this is the region of space that I control as a planet, then they're gone. They're no longer associated with that planet.
Right. So I see what you're saying, that it's not just a matter of, if you've got a honkin' great planet close to a star, gravity is much stronger and things are moving much faster, and that might make things a bit less stable. But what you're talking about is, but we've got to get the planet there in the first place. Something had to do that, and that's inherently itself a pretty unstable situation.
Yeah.
Things are going to get flung off.
And when you get there, you still have to hold on to it. I mean, it's the three-body problem again, right?
Yeah.
Gravitationally, it's very difficult to hold things in these kind of scenarios. Mercury doesn't have any moons. Venus doesn't have any moons. This is kind of why, because the sun's there. It's quite disruptive.
Yeah. So add into that, let's bring in a big planet. Let's bring Jupiter down here somehow. That's going to be tricky. Okay.
Yeah. So anyway, those direct transits are kind of useful, but maybe limited to particular types of systems, which we'll come back and see some of. Possibly direct imaging. There's one candidate that's maybe we can actually see.
So actually looking at it with a telescope.
Yeah.
Yep.
This is quite debatable whether or not it's a planet and a moon, because the moon is supposed to be 318 times the mass of the Earth.
That seems quite...
large. I feel like that's not a moon. I know that these things need to be defined properly, but my feeling is at this point that this is probably more likely to be like a brown dwarf, instead of being a planet, it's a brown dwarf, which is a kind of a failed star, a small star, and a planet rather than a big planet and a big moon.
Right. This is a different kind of system that we're talking. Something else is going on here. It's not impossible, but as you say, it kind of depends on how we end up defining these things.
Yeah. I mean, and any natural satellite of a planet is a moon by definition.
Sure.
But it just feels wrong, doesn't it?
Yeah.
If it's the size of Jupiter or bigger.
Yeah. I mean, look, the first exoplanets we found were not normal.
True.
Right? It was just simply because they were the easiest ones to spot, which were the really, really stupidly big ones. Maybe the first exomoons that we're going to spot are going to be, that's not normal, but it was the easiest to see. So there you are. Let's go and look for much more normal ones. But anyway, we'll see.
Yeah. Right. Moving down the list. We can look at sodium and potassium from evaporation or volcanic activity.
Right.
I'm going to completely just pin that one. I'm just going to say that is, and then we're going to come back to it because that's exactly how one of the planets, moons, candidates that we're going to talk about
today. Stick a bookmark in that one. We'll come back to volcanic activity on moons.
Yep. Transit timing variations, which are basically saying if you've got a planet that's transiting a star and it transits fairly often, let's say every few days or something like that, you can measure very precisely when that transit should occur and therefore say if it's a little bit early or a little bit late, there's been some gravitational tug on that planet.
Right, yep.
Which could be from a moon.
Right.
Now, it's much more likely to have been from another planet in its own system, but possible.
Yeah. Again, if you're talking tiny effects, then there's a lot of confounding possibilities in there.
Yeah.
But it's possible. It's a way to look.
Yeah. Indeed. Microlensing. There's been a couple of candidates through microlensing, which is using the gravitational field of the planet-moon system, looking at how that bends light from a distant star, say. So light from the distant star is travelling towards us. It just so happens that there's a planet and its moon in the way that bends the light, and we get to see this kind of brightening of the background star in a very, very characteristic way.
Right. I mean, we talk about gravitational lensing on a much larger scale when on sort of, cosmological scales. You see the lensing effect, the gravitational lensing effect of, supermassive black holes or entire galaxies or clusters of galaxies or whatever that might be. But you're talking about a much, much smaller scale. That just boggles the mind. How could it even conceivably be possible to tell the difference between the gravitational lensing effect of a planet and a moon? Like, that's nuts, right?
Well, yeah, but you get a time sort of thing. So the star sort of, if you imagine it, it's very similar to how you get the lensing curves of star plus planet being the things in the middle, except now you've got planet plus moon. So you get this curve that goes up as the planet's moving in, it's increasing the lensing, and then as it's going down, perhaps maybe the little moon pops into the sort of path, and then you get this little blip just before. It sort of
it's
dies
still
off.
I mean, that still blows my mind. Are we talking about, just to be clear, are we talking about it lensing the light from the star that it's going around, or is this a different star way off in the background? No,
completely different star, way off in the background. Yeah,
okay. That still blows my mind because, I mean, gravity for a planet is still really, 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 really small. Yeah. And so seeing that lensing effect at all blows my mind, let alone that percent of a percent of, and throw a moon in there and here's what we expect to see. But sure, why not? Throw it into the list as a possible way to do this.
Yeah. I mean, the problem with microlensing is, of course, that they are one-off events. You never see the same system twice.
Yeah, of course.
They're just chance alignments and they never become alignments again.
Yeah.
So by definition, almost all these candidates are always going to be candidates because we can't do follow-up on them.
Right. But it's, I guess, as you say, it's a way to sort of identify as, okay, flag that one. Can we find another way to investigate that one because something interesting just happened?
Well, yeah, and maybe not that system, but at least it tells us that there are other exomoons in the galaxy.
I see, yeah.
Or statistics, we can do some sort of thing. Well, this many planets have... Anyway, things like that. And the last one is some light variations. This is a very dodgy one, I think. I'm not sure I'm fully on board with this one. But anyway...
Emily's got her skeptic's hat on.
Yeah,
right now.
well, I'm not really sure how it works, and it could just be my lack of understanding. But basically, some planets might have become shinier or more reflective at certain points if they've got a moon that's doing something to the plasma around the system. So it's kind of a bit of a messed up system with plasma going around with the moon.
Okay. So the interaction between the moon and the planet and the way those things are forming could, in principle, change what the reflectivity of the planet, change
so
the light that we would see bouncing off this thing, and you would then infer, oh, well, the only way that could be is if it's got a moon.
Yeah.
Okay, all right.
So anyway, those are the ways we've found these 20 or so candidates that we have right now. Some of those I think are more reliable than others.
I was about to say, is that list in any particular order? Is it in
no,
order of believable to?
No, I
really?
should have done that. Should have? And then we just and there's others and others. But anyway, coming back to therefore the two systems that we're going to talk about in a bit more detail today. Actually, three systems we're going to talk about. Let's start with the historic one because that was the interesting one, casting our minds back all the way to 2018.
Yes, episode 19.
Yes. So in that episode, we talked about Kepler 1625b.
I remember it well.
Yeah.
I don't, but
no.
sure.
Anyway, this was the candidate moon system that was based on transit timing variations. So looking at, did it arrive slightly too early or slightly too late in its transit?
Right. And I'm imagining that as, if you think of a planet going around a star, that can be, it's not always, but it can be a very, very regular thing, right? But if you throw a moon into that, I'm now imagining the moon and planet system kind of, they're orbiting around their own gravitational center as well as around the star. And so I'm imagining them sort of, wobbling their way around the star, which means that as they come around in front, that could happen slightly earlier or slightly later than if it were just a planet, simply because of the time in which
one hits the transit first.
You're seeing that particular wobble of the moon and the planet going around each other. So, yeah, again, small effect.
Well, yeah, incredibly. And I guess the only example we would probably use in our solar system would be something like Pluto and Charon. Okay. So that Charon, Pluto's moon, is not hugely smaller than Pluto, right? It's huge. And at least comparative to Pluto. And so what that means is that the central point that both the planet and the moon orbit around isn't the center of the planet, as it is with a very large planet, very small moon. It's actually outside of Pluto.
Right.
So they're both kind of orbiting around this invisible point in space. So if you can imagine that, even if they were similar mass, the planet and the moon, then it would depend on what stage they were in that orbit when they started transiting in front of the star. And so it could be a little bit, they could have Pluto go first, or you could have Charon go first, or they could be kind of lined up. Yeah. So that would be one way you could use
that'd be sort of
the
extreme end of where you've got, planet and moon almost interchangeable. They're both comparable in mass. And so that external point around which they're rotating is very external. And so that could mess things up with that timing a lot, as opposed to the case with, I'm guessing, the Earth and our moon, where that center of mass is inside the Earth still. Yep. So the Earth is still doing a wobble around that point, but it wouldn't be nearly as noticeable. No. And then it goes up from there to something like Jupiter and some of its smaller
Jupiter's
moons,
basically in the middle,
barely even noticing the fact that the moons are there. So, okay.
Yeah. Okay. Yeah. Anyway, so coming back to 1625b. So there was these transit timing variations maybe saying, okay. That was 2018. In October 2018. In April 2019, so only a few months later, another group took the same data set and did some more modelling, said, maybe not a moon, it could have a single planet kind of fits these data as well.
Okay, right.
So,
So it's a very small effect on a very small effect, and you look at it hard enough, you get some more data. Sometimes these things go away.
Yeah, exactly. I mean, we're working it right down in the very, very, we're even pushing the limits of what our instruments can detect at this point, right?
Yeah.
So
in science, it's sort of known as the uncertainties in a measurement, and sometimes what looks like, that's a really interesting effect, that looks like, a difference in timing or a wobble, you gather more statistics and that goes away simply because that's what random noise is.
Yeah, and how you treat your data from the point it goes to the telescope to the point you say, what does this transit actually look like? What time did this transit happen? That can that data treatment becomes so important, because if you treat it one way, you might get a different result than if you treat it another way, even though those are both potentially very valid ways of looking at that same data set.
Yeah, and this is really hard stuff. Like, there's entire areas of scientific endeavor devoted to just trying to understand what are the uncertainties in these various measurements. It's hard, really hard stuff.
Anyway, some later transit timing variations suggested actually maybe this planet-moon system was there. That was 2020 in August.
Okay.
So
we
revised measurements.
Went from 2018, we think it might be, to 2019, we think it might not be, to 2020, we think it might be. Mm-hmm. Yeah. It's a roller coaster, isn't it?
Yep, December 23, where another group did some more modelling, said, no, probably not.
Could we please just get this together?
And that was the most recent paper, although there's been a response to that from it's almost like two
warring factions.
Two disagreeing groups of scientists.
That's a more polite way of saying it.
Yeah. And so there's been a reply to that which says, but actually, have you thought about this? And so I think that debate is ongoing. Neither have said conclusively that there is or is not a moon around this particular planet, but equally neither is particularly backing down on their stance.
Fans of the history and philosophy of science would have a field day with this one. It's just classic case of science doesn't always progress in a very orderly, linear fashion.
No, indeed. But I mean, it's all very collegial and polite.
Sure, yeah. There's no fisticuffs or anything.
No, but it's just kind of saying, well, let's just agree to disagree until we get more data and move on.
But further underlines just how difficult this is. Like, if we can't even agree after 6 years, plus however long it took to actually get the original results in the first place, we still can't agree whether or not there is in fact a signal here. That's hard. Yeah.
So the main proponent, let's say, for this particular exoplanet having an exomoon is a person called David Kipping, who is an associate professor at the University of Columbia, who leads a research group called the Cool Worlds Lab.
Cool worlds as in, wow, that's cool, or cool worlds as in not very hot?
I suspect it's a play on words.
Okay. Yep.
So, yeah, maybe both. So the Cool Worlds Lab is quite an interesting group. So they're really looking at typically very widely separated planets from their host stars. So cool because the planets are quite far away from their host stars.
Yes.
Not these hot Jupiters and so on. They're interested in much more these, more extended systems. Now, those are interesting because they're much more similar to our solar system, right? You think Jupiter's quite a long way from the sun.
Yeah, it's quite a long way out.
So we can draw more of the analogies of the stuff we know about our own solar system. What makes them, of course, hard is that those systems have orbital periods of years.
Yes. I mean, how long does it take Jupiter to go around our sun?
Good. It's like 20-something years.
Like really long time.
A long time,
That's very difficult to get lots of data on if you're studying that system.
Yeah. So they're actually interested in another planet. I think they've kind of given up on 1625b.
Okay.
It's like,
let's put that in the too hard basket for now.
Yeah,
exactly. That one's still pending.
And there's not really a lot of more data that we can do with that one right this instant anyway. That was all Kepler data, which, of course, Kepler is not feeding us anymore. However, they've got another system which they're quite fond of, which is called Kepler 167e.
Okay.
So the E means the...
Now, the letters of the alphabet mean which planet out from the star. So it's not which one got discovered first. It's going out from that. But A doesn't exist.
Correct.
So B, C, D, E, fifth letter of the alphabet, it's the fourth planet out.
Well done.
Well done, everyone.
So fourth planet of 4 that we know of in this particular system. Now, this is a really interesting planet. It's a Jupiter analog. In fact, it's pretty much exactly the same mass as Jupiter.
Okay, so big.
Yeah, big, but it's on this much, so it's not hot Jupiter. It's not close to its star. It's on a much, much more distant orbit. It's about nearly twice the Earth's orbit from the sun.
Right, okay.
So
it's not a hot Jupiter, but it's much further in than Jupiter is. Is that right?
Yeah. So Jupiter's about 5 times
Yeah.
the Earth's distance. So this is about 2 times the Earth's distance. But the star itself is a cooler star than our sun.
Okay.
So this star is about 4,900 Kelvin. Our star's around 6,000. So cooler star. So even though that this Jupiter is a bit closer, it's going to be more or less a similar temperature, sort of similar characteristics of its position in the solar system to where Jupiter is in ours.
Okay.
And as we know, Jupiter in our solar system, loads of moons.
Loads. I mean, it's no Saturn, but it does have quite a few. How many planets does Jupiter have?
Moons, it's got about, I don't know, 60, 70, something like that.
Yeah, I was about to say,
Yeah.
I knew it was dozens.
Yeah.
But it's, yeah, I mean,
So it's got the 4
not Saturn.
famous Galilean moons, Io, Europa, Ganymede, and Callisto.
Those are the big ones.
Those are the big ones
Yeah.
that you can see with the binoculars even, actually, going around Jupiter. But then it's got, dozens of other smaller ones that have all sorts of fun names, depending on the systems that they're in. Yeah, so you'd think, actually, this is quite sensible to, instead of looking at these hot Jupiters that are close, that we don't really understand the orbital dynamics of how to keep a moon on a planet once you're that close, let's look at something that we know from our solar system is much more likely to be similar and therefore have moons. It's kind of, work with what you know.
Yeah, it makes sense. It
Yeah.
makes sense. Go and have a look under where the street light is. Yeah.
Yeah, and so this is an interesting system. It's only transits once every 3 years. It's a slow transit, so it takes a few days for this planet to go over its host star because it's so far away.
Right. Okay. Yeah. Yeah.
It's doing a long orbit. It's casual, slow.
So it's every 3 years, which is like, that doesn't give you an enormous amount of data to play with, but you've got a long time to look at it.
Yeah.
So if you get that timing right, you got plenty of data.
Yeah, that's exactly what this group have done. They've gone to JWST and said, hey, look, this is quite cool, transiting Jupiter that may or may not have exomoons. Let's stare at it for a couple of days and get its whole transit, and let's just see what happened. And they were successful in
Awesome.
that proposal.
How hard is it to get several days of JWST
Well,
time?
yeah, huge. I mean, it's hard enough to get a couple of hours.
You'd need to really make the case.
Yeah, this is 60 plus hours of time on this telescope. So, yeah, that's a pretty big deal, right? But maybe finding the first exomoon is a big deal. I'm not really sure what that tells you, but anyway.
No, but
finding the first is always
that'd be a
nice.
great press release.
Oh, yeah,
I think
definitely.
Yeah.
Yeah, so, and literally this has just happened. So the last few days in October, this is when this transit's just happened. So as we're recording this, it was a few days ago that JWST completed those observations.
Okay, so that's way too early for us to go, oh yeah, no, we've seen it, totally. You got to go through that data.
Oh,
now,
yeah,
and that's
yeah.
going to take time.
So that data may well be in that group's hot little hands right now. They might be getting very excited about it, but it's going to take months to process and really... you want to dot your I's and cross your T's on this one because there's so many candidates out there. If you really want to show that this is a real detection, you've got to have really strong case for that.
Yeah, and this is, just to be absolutely clear, like this is not looking through a telescope and going, there it is. This is tiny fluctuations in very small signals from very far away that may or may not stand up to scrutiny the more data you get.
Exactly.
Yeah.
Yeah.
So it's going to take time.
Yeah. I mean, the data embargo on its own is about a year for JWST.
Right. Okay.
So that means the group's going to has exclusive rights to it for a year, which,
Right.
They worked for that.
Right.
But maybe in a few months we can expect to see their results, even if it's a null detection, which maybe that's interesting though in its own right? Because that says when we've got this as close, I think, as a duplicate of Jupiter that we could possibly get in an easy to observe exoplanet system, not finding a moon is kind of as interesting as finding one.
Yeah. Yeah. And whether or not you're able to statistically pin that down enough to be able to say, we can't see if there's a moon, or we can see that there isn't a moon, or at least there isn't a moon bigger than this, right? You can't rule it out completely, but presumably you could rule out, like, we know there isn't something there, bigger than a lump this size.
Yeah, we can say that there might not be something the size of the Galilean moons of Jupiter.
Yeah. Which again would be an interesting data point. Wouldn't
Very
tell us
interesting, yeah.
huge amounts, but it's a data point.
Yeah, I think sometimes we undervalue null detections. And actually, I think in this case, a null detection would be worth the celebration, if you like, as much. Well, maybe it's hard because I guess
it's not nearly
it's
as cool
easier
as
to get
finding an
exciting
exomoon,
as finding the first one. But
no
sometimes
one's going to buy a cake, right? At the office, I don't think anyone's going to buy a cake.
I'd buy a cake.
Well, yeah, I guess. Okay, no one would buy a cake and like party poppers. Like no one's letting the balloons off, right? For we didn't find an exomoon. But to completely take your point, it's still important stuff.
Yeah, exactly. So that's quite cool. So that was one of our stories that's come up in the recent news. In fact, just in the last few days, of that this is happening, and so we can, I guess, sit and wait patiently.
Yeah. Watch this space.
See how long it takes the team to get through that processing and see what the outcome is of that. But it's very exciting. The other one coming back is actually 3 weeks ago or so. There was a big sort of flurry of press releases coming from Caltech, so another US institution. And this was from Team Apurva Oza and collaborators, who were looking at a system, the planet WASP-49b, and they've detected something which is quite interesting around WASP-49b. They've detected its potential signature of a volcanic exomoon.
Right. Now, this is the one that you said, let's bookmark that earlier. So this is not looking at timing fluctuations or transits or anything like that. This is something completely different. And sounds really awesome. So take us through it.
Okay.
What and how have they seen?
Well, let's start in our solar system, because this is where the inspiration and our understanding comes from. In our solar system, we've got Jupiter, and one of the moons of Jupiter, called Io, is highly volcanic.
Yeah, quite famously so. Yeah.
And it's volcanic because of the tidal forces from Jupiter's just enormity mean that the interior of the planet basically gets twisted and turned, it's heated up, and then that means that there's a lot, like full surface of the moon is volcanoes and vents and steam gases coming out.
It's quite a wild idea, isn't it? But like we tend to think of something like a moon being a cold, dead thing like our moon, right? There's not a lot going on our moon. There's no active volcanoes as far as we know, right? But don't discount the power of the gravitational force when you're close to something really, really, really big. And what that means is that when this moon is going around Jupiter, the gravitational, like the difference in gravitational force just from one side of that moon to the other and from one part of the orbit to another shifts around the actual material of the moon itself, which creates heat, which means the whole thing is like hot and active and there's volcanoes. Like, that's wild.
Yeah, it's crazy.
You kind of forget that gravity is just that.
It's just energy, isn't
Yeah.
it? It's the energy from those forces that's causing this. So you basically have a subsurface kind of lava-like ocean on Io that, as I say, erupts. And we know, we see these eruptions happening. We've flown through some of them with some of our spacecraft, right? That's
the
wild. Cool stuff.
Yeah.
And we get these jets coming out. And what this does is it creates this kind of big cloud that lags behind Io in its orbit. So it's spewing up all this stuff. It's spewing it up with such force that it actually leaves the planet. It doesn't really have much of an atmosphere. It doesn't have enough gravity to hold on to it as an atmosphere. So it leaves and it forms this kind of cloud trailing behind it, almost like a stench. You could imagine like those in your cartoons where you get this like green cloud following somebody.
Lovely, delightful. Yeah,
that's my mental image anyway. Now this cloud is made up of very specific types of chemical species, lots of sodium, lots of potassium, things that you might expect from volcanoes. It also has lots of ions, so charged particles. Those charged particles actually go on to interact with Jupiter's magnetic field, which is an interesting event on its own. But it means that you get this stuff basically that's somewhere torn between Io's orbit, and it actually expands out and it sort of pollutes, if you like, the general region of Jupiter. It's sometimes up to a few radii of Jupiter or beyond.
It's almost like a very localized version of a comet. I mean, very different reasons why it's spewing off this cloud, but you've got this thing going around Jupiter, which is leaving a trail of gunk behind it. But the point is, that's a potential way that you could actually spot something similar happening across the galaxy.
Yeah, and it's really interesting because if you think about when we do observations of systems in transit, you might want to take a spectrum, and in that spectrum you see this chemical fingerprint of what kind of atomic elements and ions you're seeing in that region. Now, the vast majority of that will be from the star, right? So stars, they have lots of hydrogen, lots of helium, but they have also trace elements, all these quote metals, anything that's
all
not,
the other stuff.
All the other stuff. And but a lot of that stuff has very significant chemical signatures that we can see, right? What's interesting about particularly sodium in this case is it's neutral sodium. Now, neutral sodium, if you just stuck a blob of neutral sodium gas, in this kind of position, reasonably close to a star, it wouldn't stay as neutral sodium for very long.
Right.
It goes through what we call photoionization. So the light from the star ionizes it and it becomes ionized sodium, so you strip off an electron. It's very easy to do. It happens in a few hours.
And you can see the difference in that in the spectrum. You can
that's
see
that's a different chemical signature to neutral sodium.
Yeah.
Because it's got a different number of electrons.
Yeah, and we know what that looks like. As that one's neutral, that one's ionized. Got it. Easy. Yeah.
So if you're looking at, say, a planet star system and you see neutral sodium, there's a big clue already there that something interesting is happening because stars don't produce sodium, right? They don't produce neutral sodium. There might be some neutral sodium in an exoplanet's atmosphere, but it would be ionized very quickly.
Right.
So therefore you must be producing it somehow.
if you're seeing noticeable quantities of neutral sodium, it's coming from somewhere.
Yeah.
Something's making
You've got a mechanism that's making it and sticking it there so you can see it, because otherwise it would just be gone.
Yeah.
Right? And so that's interesting. And it's very difficult for planets to just be blowing off neutral sodium. So what we infer from that is there may be something like a volcanic moon, or at least a volcanic system somewhere that's producing all this neutral sodium. So there's some energy, right? It's energy in the system. There's got to be something like what's happening to Io, whether that's from the planet or from the moon. There's got to be these tidal forces that are generating geological activity and therefore neutral sodium, right?
But that's
already the first.
That could be the planet, though, right?
It could be the planet, and it could be that the planet's so volcanic that it's just spewing stuff everywhere. What is different here is that you can see this sodium cloud, and when we look at spectra, we're getting all sorts of really cool pieces of information. We're getting not only the chemical fingerprint, but we get a velocity signature from that as well.
Right. Because when you look at the spectrum, if you make the assumption that everything's standing still, then you can see what the frequencies of this fingerprint, the lines in that fingerprint, the spectral lines, the frequencies, you can see where they are. But as soon as things start moving, those lines shift. And so from that, you can go, okay, I know that that's, for example, neutral sodium, but from the amount that it's shifted, I can see how fast it's going and in what direction. Right.
And we have some reasonable idea of how fast the planet should be going, for example, and its direction, because we're seeing it transit. Right. What we're seeing here is that the only way, if there was just a general sodium cloud just sitting there for whatever reason it's sitting there,
let's say for the sake of an argument,
we would expect it to be moving towards us. It would be blue shifted, and that's because of the sun's sort of general pressure, the solar wind coming, or the stellar wind coming from that star. It just pushes it towards us.
Right.
What we're seeing in this case is that cloud of sodium. When we know, I'll come back to why we know it's a cloud, but this bit of sodium is moving towards the star.
Okay, that's the wrong direction.
That's the wrong way.
So so just so that I'm clear in my head, around this star that we're looking at, there is we can identify there's neutral sodium, and if it were just there, it would be being pushed away from the star. And so if we're seeing it, it would be being pushed towards us because the star is spewing out all of the solar wind. Right? That's what stars do. And so it would be being pushed away, but it's not. It's going the wrong way.
Yeah.
Okay, so that's weird.
That's very weird. Yeah. And we know it's a clump of sodium because in this particular study, they looked at 5 different transits. Sometimes you see the sodium, well, in one of them particularly, you see the sodium very, very strongly moving away from us, which is weird. And some of them you can barely see the sodium at all. Basically, you can't to the level of detection. So the sodium is transient. So it's come and gone.
Which is weird.
So that, whereas the planet is still there.
Yeah.
Right?
Yeah.
So if you put all those things together, one way you could explain that would be to have an Io-like system of this clump of sort of sodium cloud that might be following a moon going around that exoplanet. That moon has moved, say, around its exoplanet towards the star. It's dragged this clump of kind of sodium behind with it. And sometimes the moon and its clump might be behind the planet. Sometimes it might be in front of it, making it harder to spot. And sometimes it's a bit easier because the light from the star is shining straight through that cloud.
Right. So, I mean, this is almost sounding a bit Scooby-Doo. There's a lot of different pieces of evidence here, and you're trying to come up with what's a plausible explanation for something which is not what we would expect to see, which is still a way away from we've seen an exomoon, but it's a plausible explanation that you then need to, okay, let's push that harder. Let's test that some more.
And this is a wonderful example of some of these things we've talked about many, many times, of where, the press releases are amazing for this. You see all these wonderful artist impressions of like these volcanoes spewing out stuff off this rocky lump. I mean, of course, we don't know anything about any of that. And in fact, the paper itself, I mean, let me read you the title of the paper. So the title of the paper isn't, hey, here guys, we found this cool exomoon volcanic blah, blah, blah. It's awesome. It's redshifted sodium transient near exoplanet transit.
So this is where the media office at the university has gone, okay, so in 5 words or less, explain to me what this is about. Exomoon, fantastic. Okay, bring the artist in. We know what we have to draw now. It's like, no, we haven't seen that. Doesn't matter. Get the press release out.
Yeah. So, and as is often the case, I think we spoke about this quite a lot with the detection of phosphine on Venus. The paper is much more tempered. It's kind of saying, look, we found this signature. It's weird that it's moving away from us, this thing. I mean, we could explain it this particular way. Maybe that's the best way with a natural satellite, as they say. The word moon is not used in this paper. But I mean, really, what we're saying is this is a cool detection, and
the scientists are working in a very different currency from the media office there at that point. But I mean, you totally get it. Like, you can't fault them on that.
No.
And the interesting thing about the story is that, I mean, it doesn't really matter how likely or unlikely it is. The hypothesis is this could be what's happening, and that's exciting. That's really interesting, and you've got to sell that story.
Yeah.
Right?
And it's a candidate system. I mean, because of this, I mean, the detections in themselves are very odd, but the detection of at least the bit that's moving away from us, that particular detection is quite strong. Some of the others are a little bit weaker. So it's more of a case of let's get some more observations of this thing. We're in a funny sort of world of exoplanet science, I think, where we're now shifting a lot back to ground-based observing from space. Now, I know James Webb, and I'll come back to James Webb because that's doing a different kind of job. But when we had Kepler, and even with TESS, right, these 2 space telescopes finding exoplanets, they're doing great jobs. They're finding them using photometry, which means just measuring the brightness of things, right? So they're measuring the brightness of stars, looking for these little dips. They can look for transit timing variations. They can look for moons that might cause extra dips, all that kind of thing. What they can't do is do the spectroscopy, which is the chemical fingerprint stuff.
Yeah.
That, and if you want to do that properly, it requires huge instruments, right? It's not a simple thing. It's not even an instrument that you can just bolt onto the back of the next space telescope and say, here you go.
Right. And why is that? Why do they have to be so huge?
So these spectrographs are typically the size of a small house.
Right. Okay.
And the optics are such that they are so precisely aligned that as soon as you shove it on a rocket...
Yes, that's going to mess everything up.
Yeah. I mean,
getting through the atmosphere is hard.
Yeah, exactly. So they're just not suitable for spaceflight as they currently the technology exists for
and
these things.
So that sort of thing has to be ground-based.
Yeah. So we talked about some of the most famous ones of these harps is obviously kind of the gold standard for some of this work, but there's others with the Very Large Telescope, I think Espresso and things like that. So we're coming back to the ground and using these wonderful ground-based instruments to do these precise measurements of the chemical species of exoplanets, generally in the kinds of work like finding neutral sodium. But yeah, I mean, James Webb is slightly different in that it does have some spectroscopic capability. So I shouldn't be too quick to write it off. It's just nowhere near at these kinds of resolutions as well.
So would it be a case of James Webb being able to say, we should look harder at this because I've seen, tantalizing evidence for something. Quick, turn your ground-based spectrometers towards this thing. Yeah. You can get some nice spectra from James Webb, mostly in the infrared, because that's where James Webb is obviously geared up to. That's its wheelhouse. Up to look, yeah. But some of these things that you might want to be interested in are not in the infrared. So sodium, the sodium doublet's quite famous, right? It's in the middle of the optical. It's kind of yellowy colour. Yeah. Very, very famous, very closely spaced set of emission lines. Really identifies sodium. You look at it you learn this as an undergraduate physics student. So that's sodium. I don't know any of the others, but I know that one. It's a really, really easy one to spot. So looking at neutral sodium, that's a nice one to be looking at. And a couple of lines that I'm going to be looking at quite a lot in the next few months, particularly, a calcium at what we call H and K, so singly ionized calcium, and they're in the blue. Very, very blue, actually, just slightly beyond kind of what we can see blue. And they're very important for lots of different things that I won't spoil the next maybe couple of episodes on, but very exciting exo work there as well. Okay, so, it's been 6 years since we really first started down this exomoon path. And I don't know that either of us at the time really expected that it would be 6 years before we'd be doing a major update. I don't know about you. I kind of felt like we would have definitely nailed down one by now. But what do I know? Turns out it's really, really hard. So Emily, how would you kind of sum up the state of play on this particular area of astronomical research? Where are we on exomoons? I think we're on the cusp of finding them. I think it's very interesting that we're on the cusp and that they are so difficult, given that we're quite good at finding exoplanets. Yeah, we're really good at that now. And as a tantalizing sort of look forward, we're also quite good at finding exocomets. So comets going around other stars. Wow, that's cool. That's so something I haven't heard of before. We can do exoplanets. We can do exocomets. Exomoons still in the very hard basket. Still really hard. Well, look, as you say, as a tantalizing little look ahead to what will become a season here on Syzygy of exo stuff. There's a lot to look forward to. Do you reckon it'll be another 6 years before we have another major exomoon update, or are you more optimistic than that? I think we'll find out. That's a hard question. Go on, put your money on the table. Yeah, I think they're hard. They are hard. Yeah. Well, Emily, it's really good to be back. It's fantastic to be back in this season of exo stuff. I'm really excited. There is one thing from that episode 19, which we haven't even touched on yet, which is when are we going to see an exomoon? Oh, well, yeah. We do need to. That's a whole other level. That's a moon, going around a planet, going around another star. I reckon we've probably got another decade minimum before we get there. Well, I think we might find something in our solar system first. Do you reckon? Yeah. Ooh. Well, it depends on how big you want to be. If you've got I'll take anything. I'd take anything to get a moon. I think that'd be awesome. In some ways, we could have an artificial moon when we go back to the moon, right? Yes, I guess so. If we could put something in orbit around the moon, then that's a moon. Yeah. All right. Well, something to look forward to. But anyway, it is very good to be back. Emily, if people wanted to get in touch with us and say, hey, nice to hear you on the airwaves again, and here's my opinion about what I think is going to happen with exomoons and exoplanets, then they can get in touch with us in a whole bunch of ways. Can you remember any of them?
I can. I think the website, I know it's still up and running and doing very well because I looked at it today. It's syzygy.fm, syzygy.fm.
That's right. And on there, you can find all sorts of stuff, all of our past episodes, all the way back to episode 19 and beyond. And you can also find a little contact form where you can send us your questions and your comments and your thoughts. You can also find us on various social media type platforms. We're on Facebook, we're on Instagram, and other places as well. Just search for us. Go to a website, though. That's the main place, really. But listen, if you want to support the show, there's a bunch of ways that you can do that. First of all, just keep listening. And to everyone who has been listening throughout this modest hiatus that we've had in the show, thank you. Thank you so much. And tell everyone we're back. Tell your friends, tell your family. If there's someone out there that you think would be interested in exomoons, tell them syzygy.fm is the place that they need to go. But the other thing that you can do if you want to support the show is to become one of our paid up supporters over at patreon.com/syzygypod. You can join a handful of other people who keep the show running, keep the electrons pumping through the website for the cost of, a coffee or so a month. You can help us to do the things that we do. But whether you're a paid up supporter or you're just a listener, it's really nice to know that you're out there on the other side of this. So thank you so much for listening. Emily, I'm really looking forward to the rest of this season. It's going to be a lot of fun.
It's going to be extraordinary.
Oh, but I'm not really looking forward to the puns. So thank you, everyone. We'll catch up with you soon. See you later, Emily.
Bye.
Bye, everybody.